Now the flip side of ionization energy is going to be electron affinity. With ionization energy, it was how hard is it to steal an electron. Here it's going to be the opposite case, and that's how comfortable are you getting an extra electron? How hungry are you for it? And that's what we're going to be talking about with electron affinities. Now, of course, we're talking about hungry, which in atom speak is how much energy do you get to relax by taking on something. So if I'm not very stable, I'm going to be at some position. A good example of that would be my nice little rubber eraser here. It's at lower stability right now. When I let go of it, it spontaneously dropped into the lower state. It was willing to give up that energy. A negative change in energy is a good thing for it. So a negative change in energy is going from a starting position that's not very stable down to a more stable position. Now, if you look at this group 1, they're all going to become more stable by getting an additional electron. Now, why would that be? Notice that if they gain 1 electron from being neutral and become the -1 charge, they look just like group 2, other than the number of protons that are there. So their electron configuration becomes isoelectronic with something that's a little bit like a noble gas. Not too bad, but it's got the s orbital totally filled. Yeah, the p orbital is still empty, but it's a little bit like a noble gas configuration, and so it becomes more stable than you'd expect. So they're pretty happy to gain an extra electron. That also means, though, we have to balance how good they are at getting an electron with how good they are at giving one away. In other words, their ionization energy. If their ionization energy is dramatically bigger in magnitude, let's say, that way we're not paying attention to the sign for a moment. If it's better at giving up an electron, then it's going to do so. If it's good at both, but it's better at taking one away from something else, then it's probably going to end up taking one away. In this case, it's going to be better at giving up an electron. So while it can get an extra, it's even better at giving that electron up and becoming the plus charge. But it can also become the minus charge. And so we will actually see throughout the course, you can have either H plus or H minus, because it turns out hydrogen's pretty good at doing either one. It can either gain an electron or it can lose one. Now, notice group 2. We have to pay it energy in order to get it to take another electron. We have to start out on the tabletop and lift my eraser up with some amount of energy. We're lifting weights. That's how this set of atoms is going to feel as well. Beryllium, it's not feeling too put out, but calcium's really hating the idea of taking on extra electrons and everything else below it too. Okay, so let's go ahead and take a look at the other side of the periodic table for a moment. And I'm just going to clean up the screen for a moment. Here we are. Okay, how about our noble gases? Well, they're surprisingly okay with taking an extra electron. Yeah, you've got to convince it a little bit. But we're talking about the kind of convincing that you have to do with your friends when you're at the pizza place and you've had enough to eat. You're happy. But they say, hey, let's get another pizza. And you're like, I don't know. Yeah, all right. That's a noble gas for you. It was already happy with its 8 electrons. It was already totally full for its valence level. But it is willing to take on additional electrons. And that analogy is not terrible because when it does take on the extra electrons, it's probably not going to own them by itself. It's not going to eat them by itself. It'll share it with the table, but it doesn't want it by itself. So what we'll probably see is that if it's going to pick up any extra electrons, it's probably going to do it by sharing the electrons, not by stealing it. And that's going to be a big deal when we're deciding in a couple chapters about whether it's becoming an ion or whether it's doing a covalent sort of a bond. Now, these two groups, you notice, have pretty big negative numbers. It becomes much more stable by picking up the extra electrons. That's why we expect that we're going to end up seeing things like F minus or Cl minus or just generically X minus. Anything in this column is typically going to end up with a -1 charge and look like the noble gas. Anything in this column is going to be X double minus. Just about everything other than nitrogen is likely to end up as triple minus, but even then, remember, we have to look at both ionization energy and electron affinity to predict what's going to happen. This is just one of our measures and one of our periodic trends that helps us figure out what's going to happen. The rest of this section of nonmetals and metalloids and our main group metals, they're better at getting electrons. They have a decent affinity. They're not really good at giving them up. What I can tell you is that means they're probably going to be good at sharing electrons, and that's going to come up in later videos. Now, negative electron affinities. Remember, that means that the atom plus an electron is more stable than the atom was by itself. Also, positive electron affinities mean we have to pay the atom to take that extra electron. We have to give it energy to take the electron at all. Now notice that our reactive nonmetals are going to be things that can gain electrons really easily. These can gain electrons really easily, and they're also not going to lose electrons very easily. So as a result, they're typically going to end up becoming negatively charged, so these are all going to end up becoming anions. Anion, remember, that means it's going to have the negative charge. Our reactive metals, however, sometimes can take an electron, but generally they're going to be better at losing it. And we saw that with ionization energy. It's easy for them to give up the electron. They can sometimes take an electron too, but generally they give them up. And that's why these are nearly always going to be cations, in other words, a plus charge. Now our noble gases typically aren't going to do anything at all. Sometimes they're going to be willing to share an electron with somebody else, but that's not their normal mode. Normally, noble gases blow off the idea of changing how many electrons they've got because their ionization energy is insane. They have a minimal electron affinity. They just kind of shrug and say, "No, I'm happy as I am. Leave me alone." That's a noble gas for you.